B.2, Quiz 2 questions, Part 2, question number 4 through number 6. Number 4, we can always apply the limit technique. Limit technique in calculus to compare two growth functions of algorithms. Remember, when we talk about the limit technique, I said limit technique has a limitation, right? Yeah. So what kind of limitation? What kind of limitation? Because the limit of what? The limit of the ratio of two growth functions. May not exist. May not exist. And I give a counterexample, right? Yeah, so here I do not describe that example. You can find it in the video, module 2. All right, if the limit does not exist, what should we do? Use inequalities. So then we can use inequalities. Okay, yeah. This method mainly for the big theta case. Big theta case. Because for other cases, the limit could be 0, could be infinity. Yeah. So we can still use the limit technique, right? When limit equals 0, limit equals infinity, we can still use the limit technique. But if two functions has this kind of relationship, then the limit technique may not work. So that's the main problem. Yeah. All right, so not always. Answer is false. Yeah. All right, next question. Which of the following asymptotic notations contains all those functions that have the same level of growth? Here you need to understand the meaning of same level of growth. Yeah. Big O notation first. This gives us the, upper bound, right? C, we just use C, right? Big theta notation give us both upper bound and a lower bound. All right, yeah. Big omega notation only lower bound. Here you can see for the big O notation, big omega notation, they only have one-sided bound. So either upper bound or lower bound. Yeah, one-sided bound. But big theta, two-sided bounds. Two-sided. Okay, yeah. In that case, so we can treat these two functions, f of n, g of n, same category. same growth category. Same growth category. Okay? Because if this is true, then we can write another equivalent inequality like this. Okay? Yeah. For example, G of n less than G of n. We know both C1, C2 positive constant, right? Yeah. So we have G of n, these two inequalities are equivalent. We just use some basic algebraic properties for inequalities. So we can easily derive, these two equivalent inequalities. That tells us, this. All right, so let me write this way, okay? Yeah. F of n in big theta of G of n equivalent to G of n belongs to big theta of F of n. Okay? Yeah. So they are in the same growth category, same level of growth. Yeah. So the answer is big theta. Okay? All right. Question number 6, the last question of this video. Can we take the derivative on a function of a discrete variable? Remember, when we apply the L'Hopital's rule, so usually we need to take the limit f of n over g of n. When we apply the L'Hopital's rule, I said we should not do it on the discrete variables. We should do it on the continuous variables. So we work on continuous variable x. Then we can take, but remember, for the indeterminate form, not indefinite, indeterminate form, we can apply the L'Hopital's rule, take derivative f prime over g prime. So with that background, then I ask you, for a discrete variable, can we take derivative on a function directly? Because answer is no, you cannot. You cannot. The definition of derivative, if we go to the definition of the derivative, so here, let me recall that. How to evaluate derivative at certain point x0. Okay, so we take limit delta x approaches to 0, f of x0 plus delta x minus f of x0 over delta x. This is the definition of the derivative. Recall, okay, here when delta x approaches 0, small change approaches 0, all the values, all the x0 plus, all those small delta x values, all the function values must be defined, right? Must be defined, at least, right? So then we expect the variable must be continuous variable. Otherwise, if it's not continuous variable, then maybe at some points, the function value is not defined, right? Not defined. Then we cannot get this definition. It does not exist. Okay? Yeah. So for that reason, we must work on continuous variable. All right? Yeah. That's the problem. All right. So we finish 3.2.